This is the last lecture of the fourth module, which is also the last module. So what I intend to take the time today is to take, first of all, answer questions. And throughout the time, you can keep on asking questions and I'll immediately take them up. I'll also take time to summarize what we have learned in the four modules and take a couple of examples to show how we do problem solving. And we'll end the hours by saying we've learned something. What is more to learn in thermodynamics? So we'll stop it. We'll take a little time to talk about that. So, for some questions that were pending since yesterday, so let's take those up first. There's a question about what are the materials used in boiler and turbine. Okay, so if you look at coal-fired boilers or oil-fired boilers, the tubes carry the water and these are subjected to high pressures. And by high pressure meaning whatever the pressure we get in the thermodynamic analysis, that is the pressure of the water inside the tubes, and this could be anything like, for small boilers this may be about 100 bar, and for large power boilers these days 280 bar, 300 bar is not uncommon. The thing is, because you have such high pressures, we need to make whatever the tube or the cylinder or the container whose diameter is small because of stress analysis. If you recall your solid mechanics, that larger the diameter, the stresses increase in proportion to the diameter, and the thickness of the wall that you require to make that device keeps increasing. So these devices which are at high pressures, if it's just a vessel or a tank, that is called a pressure vessel. And all these parts in a boiler or in a power plant or any other cycle which are subjected to high pressures, these are called pressure parts. The common materials that are used, these are lots of carbon steels of different types. And it's not just the fact that they are of this type of a material, but also that the way we make these affects their quality, also affects their life. So most of these things, they are firstly made out of small diameters. So diameters are relatively small. Of the the tubes in which water is boiled and evaporated, those tubes could be something like maybe 50 to 70 mm diameter. And the pipes that carry the steam from the boiler to the turbine, these could be like 350 to 400 millimeters in diameter. And to get the best mechanical properties out of this, these are made by hot rolling. That means you make a tube which is heated up, and then you first extrude it, and then you expand it, turn it, bend it, everything while it is hot, what you have learnt in metal forming, and that's how we get these tubes. So we cannot transport very long tubes to the site, so these tubes are made in lengths which are transportable, which is the length of a railway freight wagon. So all these tubes go to site, and at site then these tubes are put together and welded by hand. After welding is done, they are radiographed to see if there is any defect, and after that they are finally filled with water, which is pressurized more than the design pressure, what thermodynamics told us, to make sure that there is no leak. So that's what is done. Most of the tubes and pressure parts, these are of carbon steel. And how we selected these is that we needed to go to the temperatures that our cycles are telling us, like 560, 600 degrees Celsius, that type of temperatures. And our objective is that they should have strength and integrity at that elevated temperature continuously, year after year, for maybe 20, 50, 30 years. That is the whole thing. So that's what's done in boiler tubes. The turbine story is quite different. Okay, when I talk of boiler here, this boiler includes the fossil-fired power plant. It also includes a combined cycle power plant. If you have, I'll just explain what a combined cycle power plant is. We come to the turbine now. First, you have the steam turbine, and these are alloy steels. Alloy steels for the shaft and the rotating parts, the shaft, blades, and rotating parts, and different types of steels for the casing, the stationary parts. The real high-tech part are these rotating parts, because they are not just at high temperature, but they are also rotating, they are transmitting torque, and if you got a lot of blades on it, they would also be vibrating. So these are alloy steels. Typically there will be tungsten, vanadium, chromium alloys, and almost all of these are made by forging. Then they are machined and finally assembled to make a complete rotor. The casings are produced by casting, and after that they are machined, the blades are put in it, and the turbine gets done. So this is the material for steam turbines. Gas turbines, the temperatures at which they operate are much higher. So this temperature we are saying is limited to 565 degrees Celsius, the highest anywhere. And I mentioned that there are efforts to design it for a temperature of 710 degrees Celsius. So what happens here is steels are of no use. They do not maintain their strength at this elevated temperatures, and so the materials that are used here are various type of nickel-based alloys, nickel and cobalt alloys. Make such large components on a big scale is something what technology development is all about. So that's being researched now. It will be some time before we get that the high temperature parts of the turbine will be made out of these. Examples could be, say, what a family of materials called Inconel, different grades of Inconel that is there. And once the temperature in the turbine after expansion has reduced, then we make parts out of alloy steels. Gas turbines have an entirely different story, because the temperatures here, as I mentioned, are much higher than this. 1400 degrees Celsius, 1600 degrees Celsius stationary gas turbines are already in use, and there are gas turbines with like 1800 degrees Celsius. These temperatures are above the melting point of either nickel cobalt alloys or any steel alloy. So it is not just enough to make the material and the blade, but we also have to actively have a method of cooling it. Otherwise, it will just melt away. So what is done is that as the flow takes place over these turbine blades, this is a typical sketch of a turbine blade. What is done in this blade is that these are hollow. At the base also they are hollow, and they sit on the rotor. So this is the shaft. This shaft is also hollow, and some of the air from the compressor, say about 700 Kelvin, 800 Kelvin, 900 Kelvin temperature, instead of going to the combustor, bypasses that, is pumped through the passage in the shaft, comes in, connects with openings inside the blade, comes into the blade, moves through hollow passages inside the blades, comes out either from the top, or there are small holes on the surface of the blade from which this air comes out, and what it does is that this air goes over this, and right next to the surface forms a small blanket of cool air. So if you have to take a top view of this, one can say that this is the blade, these are the passages, and say here and here we were throwing out air over this. So this air came out and it went over there, this air came out, the flow over the turbine blade is like this. So this cold air is going over there, and outside this is the hot gases that are flowing over here. So the temperature here is what I mentioned at 1600, 1800 degrees Celsius. This air that is coming out is about 900 Kelvin or something of that order. And so the surface of the blade has, some air is also put out to the back part here. So this is sort of an open here. So there you have a blanket of cold air surrounding this blade so that the material temperature in this does not go anything like 1000 degrees Celsius or even less than that. To further reduce heat transfer to the blades, one more thing is done. So these blades are all made of nickel cobalt alloys. Okay, so that's one. The second thing, they have a small thin coating on the top, few hundred micrometers thick, and this coating is made of certain ceramic, typically zirconia oxide. Ceramics have very, very poor thermal conductivity, so they reduce the amount of heat that will go into the blade. So we like to have that. The trouble is, first, ceramics are very, very brittle, and in a machine like this, if it comes off, that's a problem. The second thing is, if the blade is made of nickel and cobalt, and this is zirconium dioxide, there is no way that we can make ZrO2, zinc of zirconia, to stick to a nickel cobalt alloy. So the process of making zirconia substrate on a nickel cobalt alloy, this is extremely complicated, and we build layers and layers of different elements which stick to each other, and the last element in that is zirconia oxide. So this is a very, very, so this whole thing, casting of this blade is a very sophisticated technology. That to get better mechanical strength, you do not like to have grains in the material like you've learned in your, say, casting or manufacturing process. So they try to make this and cool it in such a way that the whole blade does not have grains but is a single crystal. That has very, very good mechanical properties. Then there are cooling passages, and then there are ceramic coatings on top of that. So gas turbine blades, aircraft engine blades, especially in the first 2-3 stages where temperatures are very high, this is what is being used. And the research that people are doing is that can we make the entire blade out of ceramic? And that's a huge challenge because ceramics cannot be processed by any of the conventional manufacturing techniques that are taught in a typical manufacturing course. So that's about blades used in turbines. So that was one question. The next question was, what about supersonic flow in a nozzle? Hey, so this is what it is. When you say supersonic flow, what we mean is that the local velocity is greater than the local speed of sound, or C. And I'm using the word local because if you have, say, a nozzle, as the flow goes through it, its temperature is changing. So when the temperature at different locations is different, the local speed of sound is also different. So the Mach number, this is, we have defined it as the velocity of the fluid divided by the local speed of sound. Now the reason why this thing comes up in the context of nozzle, and I'm taking it here, say, is that if you have a nozzle, which I have drawn like this yesterday, the flow goes in there, it comes out at a higher velocity, so pressure decreases, velocity increases, and that behaves like a nozzle. But what will happen if at some point, so we are assuming firstly in this, that everywhere Mach number is less than 1. That means this is the flow is subsonic. This behavior is correct. And the same is case with what we do for a diffuser yesterday. If you have a passage in which area increases, and it need not be a passage like this. I showed you yesterday that if we make a turbine blade like this, 2 consecutive blades, they produce, you can make the shape in such a way that the areas could be equal, or areas in the direction of flow could be decreasing, or areas in the direction of flow could be increasing. Either is possible. So here also, when we said that the flow goes in, pressure increases and velocity comes down, we have also assumed here that this is a subsonic flow. The opposite happens if the flow is supersonic. So this begins to behave like a diffuser and this starts behaving like a nozzle. So what happens is that if you have a converging nozzle passage, say it is like this, and at this point we have Mach number equal to 1, then if you further decrease the area, it will not behave like a nozzle, but it will behave like a diffuser, and so pressure will start increasing. So now you ask that, well, I want to accelerate the fluid to an even lower pressure than what I could get here. I can't get this. Then what you do? So then you put a diverging section, and this part behaves like a subsonic nozzle, and this part is designed to behave like a supersonic nozzle. So what happens is that in this part we say Mach number is always greater than 1. We are accelerating it even more and more. So as Mach number and the area is, then here pressure will continue to decrease and velocity will increase, but this is a precondition for this behavior to take place. So to accelerate fluids to velocities much greater than the Mach number, local Mach number, possibly a combination of these two is required. The opposite happens here, that if we want to decelerate the fluid, a supersonic fluid, then this word will not do the job. A passage like this, if Mach number is greater than 1, this will start acting like a diffuser, velocity will keep going down in the direction of flow, and pressure will increase. The thermodynamics is the same, and we have not gone into the detailed thermodynamics of it, but the thing to remember is that as there is no discontinuity in the properties, conservation of mass and energy, the way we have learned, will apply. All these flows, in the ideal case, as we have discussed, these are all isentropic flows. And we have seen yesterday how we could not isentropic. It is a hugely irreversible process. S will increase, and so the isentropic flow condition can be done before the shock and after the shock, but not across the shock. We will not go into full details of what shock is. It's a whole different topic by itself. That there is the need or requirement. We will have a separate module on this type of flows. But from our perspective, what we have learned in thermodynamics, this is fine. That we could get we could say that there is a nozzle and expanding it to a pressure where Mach number actually becomes more than 1. But thermodynamics does not tell us what the shape of it we have to get from compressible flow thermodynamics.